Hi everybody. Again, thank you for joining the webinar today. It's selective extraction from methyl mercury with quantitation by combustion atomic absorption, or CAA. Korean food safety methyl mercury test method 9.1, 9.2, second law, with Teledyne Leeman Labs Hydro 2 C combustion analyzer. So total inorganic and methyl mercury determination, that's really important to monitor uptake for bioaccumulation in the ecosystems, whether it's flora or fauna. And by doing this, we can look at the risk and mitigate human exposure by adequately assessing the contamination in the environment. The World Health Organization states that it's toxic to the nervous, digestive, and immune system, and that's both organic and inorganic, and it's a huge threat to fetal and early childhood development, and it tends to severe neurological issues with the fetus and then also the child as they grow up. Quantitation and or qualitative research for mercury, both species, inorganic and organic, in the environment is an extremely valuable tool. So if we know these values, it's possible to model the mercury transport and fate in the global environment. So if we know the starting species, so say it's inorganic, there's a ton of inorganic, and we can determine those typically by thermal desorption. You can take those species and model how fast it's going to go into methyl mercury, depending on what else is in that system, bacteria and so forth. So in some cases, if we know the origin of the species, we can mitigate it and prevent harmful exposure to methyl mercury just by simply knowing the starting species and the kinetics and the route it takes to get to methyl mercury in whatever it is, fish, plant, food, and so forth. So in this presentation, I will discuss the capabilities of the CAA system for determining methyl mercury by selective extraction with combustion atomic absorption detection. So a novel method developed by the Ministry of Food and Drug Safety in Korea, notice number 201898, methyl mercury test 9.1.9.2.2, specifies selective extraction with combustion for determination of methyl mercury. The method scope. So it applies to all foods where the standard of all foods where with the standard of specification of methyl mercury has been set. So the analytical principles of this method, you take a known sample, weigh it, and you're going to pre-treat it with sodium chloride, a 3:1 solution of hydrochloric acid, toluene. And then you're going to take that solution and you're going to centrifuge it at 3,000 RPMs. And then from there, we're going to extract the toluene fraction into an L-cysteine solution. So that's the fraction that we're going to analyze. The L-cysteine solution is the analytical portion of the extraction. And also on this system, I've equipped the Hydro 2C combustion system with an external dryer just to assist with mitigation of any free organic vapors and stuff that may come through the system. And then the quantification for the methyl mercury is calculated using the simple mass conversion of mercury to methyl mercury. And it's from the total mercury, and it's on a dry basis. So the Hydro 2C is a combustion atomic absorption system. Dynamic range is typically 0.05 to 1,500 nanograms. give or take. No sample treatment, combustion to Hg0 is pre-concentrated on a gold trap, so we don't need stannous chloride, sodium borohydride, and the light source is 253.652. So it's pretty simple. You load the sample into the boat, inject it into the system, dry, combust, purify, remove moisture, collect, elute, and detect. We have a 2-cell system that has mirrored setup in the spectrometer, and it's a 10-to-1 ratio for the large cell versus the short cell. The apparatus that I needed for this extraction process and method, 40 mil clear volatile organic analysis vials, or a VOA vial. I used 16 of them. The method really didn't spell out a lot of this information. It was just kind of basic, so I had to review it and then use my knowledge to find the best fit to make the method work well. Vial rack, centrifuge, capable of 3,000 RPMs at 20 degrees C. Disposable single-use plastic pipette, transfer pipettes, air displacement pipettes with tips, 10, 5, and 0.1 is what I use. A 25 mil glass graduated cylinder. This is extremely important. It's for distribution of the toluene. Top loading balance, I just used a 1 milligram readability, which is fine. Small spatula, and then an arm shaker from Fine PCR, a company in Korea. It's called the ASH3. So this may or may not be needed, but when I started down this path, I was looking for something to help with automation of the method. And I came across this company at PitCon in 2019, 2020. No, it was 2019. And then I investigated and worked with the company to modify their shaker with a special rack, custom rack for me to hold the 40 mil VOA vials. And the part number for the rack is R-407. We'll get into all the Y's and the 2's about this later. Reagent. So you're going to need some distilled or DI water, 18.2 or 18.18 megohm, ACS grade toluene, sodium chloride, sodium acetate trihydrate, sodium sulfate anhydrous and hydrochloric acid, trace metal grade, and L-cysteine monohydrate, 99% pure with a formula weight of 175.64. To prepare the solutions you're going to need for the extraction, it wasn't really difficult at all. So HCl, we're going to use a 3-to-1 HCl DI water mix, volume, sodium chloride 25% weight volume, and then the L-cysteine solution. So that consists of 1 gram of L-cysteine, 0.8 grams of sodium acetate, and 12.5 grams of sodium sulfate. So what I did was I placed 100 mils in a Teflon bottle and then added the L-cysteine and then swirled a little bit and then progressed forward to the sodium acetate and sodium sulfate with gentle swirling between each addition to get the solution to start to dissolve the chemical. And then once that was done, I just capped and shook it vigorously to get it all in solution. And it turned out very clear, like drinking water. So we need to determine a moisture on each non-duplicate sample. So in my case, I only had to do 1 moisture because I was running standard reference material. The same material for all of the extractions. But if you're having multiple samples, you do have to have a percent moisture on each sample that you're going to run for this extraction. And it's because our final mercury calculations are on a dry basis. So weigh the sample into the 40 mil clear vial, 0.25 to 1 gram, record weight, and you also must include a control blank. So the control blank gets run through the entire process start to finish to include the centrifuge of the samples as well. And then for convenience, so I labeled my vials E through whatever, and in my case, I was running 8 of them, and the 8 was limited by the centrifuge. So I labeled the extraction vials E1, E2, and so forth, and then I labeled my sample vials as SX1, SX2 to correspond to the extraction vials, so I knew exactly where the solutions were going at the time. Once you weigh that sample, the start of the preparation, you're going to add 10 mils of the 25% sodium chloride. You're going to cap and shake for approximately 2 minutes. So the arm shaker really took a lot of the stress off me. Otherwise, you only have 2 arms, so you're shaking 1 vial in each arm so you can see the addition of the time and also the inconsistencies in shaking. If you're consistent in shaking, then it's probably not an issue, but it's just the added time. So I loaded it onto the arm shaker, and it made short task of this process with uniform shaking. So this is the arm shaker in process here, shaking the 10 mils of the 25% sodium chloride solution with my sample weight. The next thing you're going to do is you're going to add 4 mils of the 3:1 HCl. That's a quick and easy addition. And then you're going to add 15 mils of toluene. And this part, you want to use the glass graduated cylinder. And we don't have to be extremely precise because the precision is going to come on the other side when we add the L-cysteine to the sample. So I used a tool, so another BOA vial, to fill the toluene because it's a bigger bottle, and then I could fill the graduated cylinder up to 15 mils, and then you look at the meniscus and you get very close to 15 mils. Not precise, but exact enough, I would say. So then you want to cap and shake by hand for a few seconds. The solutions at this point are going to start to separate. Now you want to cap them and shake them vigorously for 2 minutes. And for this one, I also used the arm shaker so I can shake all 7 tubes at the same time. The arm shaker holds 7, so the control blank, that's just a manual shake, is what I use. Then you want to place these solutions into the centrifuge. So you place the toluene prep samples into the centrifuge, and you also want to ensure that now you include the control blank. In my case, like I said, it was the centrifuge holds 8, so that's where I was limited to the amount of extraction samples I could prep at one time. 20 minutes on the centrifuge at 3,000 RPMs, and you want to hold that temperature above 20 degrees C. So in my case, I set it to like 22 or 23. So anywhere between 20 and 25 is good. Then you carefully remove the sample vials from the centrifuge. So you want to do this without disturbing the solution layers. Honestly, the solids are pretty much packed into the side, but still you want to lift them out carefully and then place them in your rack gently so you don't disturb any of the layers. Now you want to transfer the top layer, that's going to be your toluene layer, from the extraction vial E1 to the sample vial, which is going to be labeled SX1. So it's a 1-to-1 transfer to those clear 40 ml BOA vials that are going to be used for the final sample. Sample preparation. So here's what I found out. So it works best to use the polypropylene type transfer pipette. Mine, I believe, were 2 to 5 mils, maybe 5 mil bulb. But it works best with that vial slightly tilted. So I'm at about a 45-degree angle, simply because I can see where the pipette tip is going into the vial, and then it's easier for me to extract it. So this is somewhat time consuming based on the pipette tips I had, transfer pipettes I had in the lab. I think if you had a larger one, you could speed this process up, but I just went with what I have, or what I had. So the single use worked really well for this. And then here's a little tip. So if the pipette pulls up a small portion of the aqueous layer that's at the interface, then you simply just hold your pipette, transfer pipette vertical, and let the layer separate in the pipette itself, in the transfer pipette. And then you can discard the bottom layer, which is going to be your aqueous layer, and then your top layer is going to be your toluene layer. You can add that to the sample vial for the L-cysteine addition. So it worked really well. So I was able to get probably 99.99% of the toluene out of the solution this way without getting aqueous solution into the mix. Now you're going to add the 5 mils of L-cysteine. So this is where you need to make sure that your pipette is calibrated, because this is your final extraction volume. So you add that to the toluene, and then you're going to cap and shake vigorously on the arm shakers, what I used, for 10 minutes. So as you can see, if you're shaking each vial by hand for 10 minutes, maybe 2 vials in each arm, so you can only get 4 done. So how are you going to add all this time? So it was very prudent for me to find this mechanical device, and I searched long and hard to find it, and then I finally found it with the Korean company to help me with these extractions. There may be others out there that would work, but I just couldn't find them. There was rotational shakers and different items like that, and I just couldn't see the fit for the method I was trying to do. So this was really a nice addition. And then once you let that happen, you want the extraction to separate. It's going to take about 10 minutes. So it's just a wait time. You're going to let them sit and separate for about 10 minutes. While that's happening, now you're going to prep your analytical instrumentation. So here, the Hydro 2C. So we have command over all of the parameters, you know, the drying time, the catalyst time, oxygen flow, the gold trap heater time, and so forth. So this is how I set mine up for this method. Drying at 200 degrees C for 60 seconds. Catalyst was set at 600 degrees C, 20-minute wait time. This is the time after the combustion that it allows the mercury to traverse through the system and collect on the gold trap. In most cases, 20 seconds is enough time for everything to traverse through the system and for a collection on the gold trap prior to desorption of that collected mercury. My decomp time was 150 seconds with 800 degrees C, but there's a caveat to this. So I also run a ramp time. And these parameters here are set up in the INI file. So I run a ramp time of 60. So I bring it up really slow, which also helps with the drying of the system. So I dry for 60 at 200, and then it's a slow ramp up to 800, and then I hold at 150 seconds at 800. So 60 seconds to get it up there, and then the hold. And then the Nathion temperature, approximately 70 degrees. So the setting for that is Nathion furnace temp 600. So that's a millivolt setting. It's not a temperature setting. And then the gold trap hold time, or hold temperature is 175. I see I have a typo in here. This should be 175 rather than 220. And then absorbance cutoff at 380,000. This is the microabsorbance units that the system looks at to determine what cell would be the best fit for quantitation, whether it's the extended 10-inch cell via mirror or the 1-inch cell for determination of the concentration of the mass of mercury in that system. So I like to set it so I determine which way it wants to go. Preparation for intermediate standards. So you're going to use these standards to make your calibration standards on the instrument. It's mass-based. So it's pretty simple. So I take 1,000 ppm, and then I do serial dilutions of that, 9 mils of 1% nitric and 1 mil stock. And then from there, it's 1 to 1 or 1 to 10 from the previous standard all the way down to 1 ppm or 0.001, I'm sorry, 1 ppb to 0.001 ppm for my lowest standard that I'm going to use to make the calibration. And then from here, since it's mass-based, you just vary the weights of those standards into a boat to give you the mass that you want for your calibration. So for example, 10 nanograms, I'm using the 0.1 ppm, and I use 100 microliters of it. And here I have an expected response and what cell it's going to go in. If we want to do 1,000 nanograms, it's a 10 ppm solution and 100 microliters of that solution with my expected response, and then it goes into the high concentration or the high nanogram cell. And I also use quartz boats because they are acidified. You can use nickel boats as well, but if you use nickel boats, I like to use diatomaceous earth to help absorb some of that acidic volume, so you don't ruin your boats as fast, because nickel will react with nitric acid, and at very low concentrations you may lose some mercury because it's going to produce hydrogen, and the hydrogen may grab some of the mercury and off gas. Therefore, I like to use quartz boats when I run the calibration. Here's an example of, not an example, this is the exact calibration for the method. So here's the low cell, and I like to incorporate the 50 nanogram response. I manually select it and put it in here, and then run a quadratic fit. And then the high cell, I manually input the blank, which is an empty boat. I run that and incorporate that into the fit, again, under quadratic. So these are results of blank up to 1,000 nanograms within the 2 cells. Sample analysis. Now let's get to the fun part. So let's take and analyze these samples. So again, once you put the L-cysteine in and shake them and mix it and extract it, your lower sample, lower layer, I should say, is the analysis fraction. So this is the L-cysteine. So that's what you're going to use to analyze for the methyl mercury. So to do that, how do we get down there? So you depress the pipette mechanism, and you go through the toluene layer. Once you get your pipette tip down in solution, you gently pull up that analytical portion of the extraction. And then you retract that pipette through the toluene layer, and then you dispense it into a conditioned or cleaned sample boat. Now here you can use the nickel boats and or quartz boat. I primarily like to use quartz boats for something that's going to be this precise, and I just like to use quartz boats. So that's a plug for quartz boats if you don't have them. I know they're a bit more expensive, but it kind of mitigates some of the issues with running a nickel bolt for trace or low weights of mercury in mass. So then you want to record that sample name and then enter the weight in the sequence as 0.1 grams because it's 100 microliters, and then run that sample and acquire the results. From here, the non-analytical samples, they all require a % moisture for final calculation. So you take a sample that you're not going to run through the extraction process, and hopefully everything's homogeneous, and you run a % moisture so you know the dry mass of that sample, so you can use that in the results. So you want to perform a methyl mercury mass conversion. You can use the following formula. So A times B divided by C times 1.075 is going to give you methyl mercury in ppm. So the Hydro 2C results are nanograms per gram. That's ppb. So that's a direct conversion over to micrograms per liter, which is also ppb. So then the results now become micrograms per liter minus the extraction blank. So there's going to be a value for the extraction blank, so we can subtract that. So we're only looking at the true mass of the sample, not anything coming from the solutions and so forth in that process. So that's A. And then extraction volume in liters, so that's 0.005, because we use 5 milliliters of L-cysteine, so that's B. And then simply divide by the dry basis of the sample, C. So that's your dry weight, and then multiply by 1.075, and that gives you your methyl mercury in ppm. So total mercury to methyl mercury conversion is 1.075, and that's atomic weight mass conversion. So for this application, it was prudent to empirically test method recoveries and precision by altering the variables of sample weight for the extraction placed into the Vold vial, and then also hand shaking versus mechanical shaking. So that was, I really wanted to take a deeper dive at that and take a look and see how it did affect the extraction percentage of methyl mercury that I could equate. So these tests, I varied the test to perform what I was talking about, varied the variables using the same sample. So I used the same sample and I varied the variables. So test 1 was hand shaking with consistent sample weight. I used approximately 0.25 grams. Test 2, I used mechanical shaking with inconsistent weights. And test 3, mechanical shaking with consistent sample extraction weights, and I used approximately 0.5 grams for this one. So here's the printout or the screenshot of the system results for test 3. So that's 0.5 gram sample, 0.5 gram sample extracted with mechanical shaking. Reported mass of each sample is approximately 23 nanograms right here. And acceptable quality control samples validated the two range calibration. So here I have in the sensitive range muscle tissue, and it's 5 nanograms per gram, and my nanograms is 0.7 gram. Remember, my lowest calibration was 0.1 gram. And then I'm also in the sensitive range, the dual cell here with the 17 nanograms for marine sediment. And then down here, coal fly ash at 1,005 nanogram per gram, which is in the high cell. And my mass of HG is approximately 90 grams in that one. So I validated the system both in the sensitive cell and the non-sensitive cell. So again, 10-inch versus 1-inch, and then the system's in control through that. Test results. So 0.25 grams with the hand shaking. My percent RSD for the final results is 9.43. I had a return concentration of 2.65, and that's 87.2%, and my percent recovery RSD was a 9.6 on this one. So here's my raw value for my control blank is 3. So I simply subtracted that from the raw extraction values reported by the system, and then that gives me my corrected value to use for the methyl mercury determination through that short equation I explained a few slides back. Here's test 2. So this is the extraction rates that are varied and mechanical shaking. So 2.59 with 85% recovery. So that decreased a little bit, but here's something that's important. My percent RSD decreased, so the precision got better. So I'm 2.59 plus or minus 0.11 at 95% confidence. And then here's the corrected weight. So I was kind of all over the board with this one, and here's the responses and based on the weights and then the corrected values. So here is test 3, 0.5 gram extraction with mechanical shaking. 2.81 plus or minus 0.606, I should say, 95% confidence. So here we got percent RSD 2.85, and the percent recovery improved to 92.4%. So my precision greatly improved by constant weight here and mechanical shaking from the previous 2 tests. So here's a cross-section, quick chart of what we're looking at. Sample extraction rate, weight, test 1, 0.25 grams, and then test 2, I varied it, and test 3 was 0.5 grams. We got hand versus mechanical shaking, and then here we have the average with uncertainty, so 2.65, 2.59, dropped a little bit, which is because of the lower rate in 2.81. Standard deviations, see the drop in here, and precision, the percent RSD, 9.43 all the way down to 2.85. So now I'm making a pretty good case for a constant weight with some type of mechanical device to eliminate some of the determinate errors that we can have from our rate of shaking by hand shaking and or not shaking for the exact amount of time that's required for the method. So kind of taking some of those errors out of it by doing the mechanical shaking. And here's the average percent recovery. So in conclusions, the conclusions on this, so the method from Korea, the Food and Drug Safety, notice 201898 methyl mercury test. It was not a difficult method. Once I did a dry run and kind of figured out what I was doing and worked out some of the items that I may have question about, it wasn't that difficult. Both manual and automated extraction can be completed start to finish in a single working day, depending on how many samples you have. The addition of that mechanical shaker, that was a labor and time-saving device. And again, it removed most of the analytical errors that may be associated with mechanical shaking. And I estimate that with that assistance, mechanical shaker, it's possible for a single lab chemist to run 21 to 28 samples in a single 8-hour shift. If you had more shakers and so forth, you could do additional samples. So in my case, it was limited basically by the centrifuge and that device right there, not so much by the instrument, because the instrument can run the sample in about 6.5 minutes. So yeah, I was limited by some of my external apparatus from the instrument. So the method recovery precision was studied by alternating sample extraction rates and the means of shaking. Mechanical shaker improved the precision and increased the rate at which the sample could be completed. So methyl mercury percent RSD improved from worst case 9.43 to 2.85%. Test 1 and test 3 used a consistent sample weight, and I observed improvement in that percent, so that can be attributed to the mechanical shaker. Test 2 was consistent shaking with the mechanical shaker and varied the extraction rates. Also showed improvement of 38.6% over test 1. So right now I'm making a case for some type of automation versus non-automation on the shaking. Varied standard reference materials were used in the test to demonstrate the stability of the analyzer. So bovine muscle, marine sediment, total mercury, methyl mercury, and or tuna fish, or in tuna fish. So I used total mercury of that one as well to look at the response of that to validate the system. NIST, trace elements, and coal fly ash was also used. The responses for all these fell within 91 to 112% which showed that the analyzer was in control. My calibration was in control for a diverse set of materials, running all those different materials. So you've got inorganic versus organic materials at different masses of mercury. Methyl mercury recoveries, again, 92.4% at 2.81 milligram per kilogram for test 3. That's falling slightly out of range, the plus or minus range on the certification for the methyl mercury in that sample was 2.88 up to 3.20. Why were we slightly out of range? I'm not really sure. It could be maybe bias from the certification. It's hard to say, or maybe I didn't get 100% extraction out of it, but it's relatively close. Lower sample weights tend to have lower recoveries, which in turn lowered the test 2 average. Rather than 0.5 grams for the sample, I maybe could have tried 0.75 or even up to 1 gram for the extraction. Whether that would make a difference in the recoveries, I'm not sure. But I think all in all, I proved that the system and the method worked relatively well, and the precision was improved with the mechanical shaker. So test 3, the results were 2.81 plus or minus 0.6, 0.06. That's 92.4% recovery. And again, the sample was CRMBCR 463 tuna fish. So it's 3.04 of methyl mercury plus or minus 0.16. So the Hydra 2C configuration for L-cysteine extraction solution, it was relatively routine and did not entail any additional complexities to get this method accomplished. The only thing I did do was I used my external dryer with magnesium perchlorate in it, and I use that routinely on the system. That's an old school drying system from way back in the 70s, 80s, and 90s before we all started using Methyl. I just like to double up with that drying system. I think it helps modulate the peak shape and so forth, and makes a just a better peak shape. All in all, easier to quantitate for the instrument all around. So it was relatively straightforward. The sample shaking automation was desirable for both expediting the prep and then also yielding improved precision of the extraction method. So the Hydra 2C with arm shaker model ASH3 from fine PCR proved to be ideal analytical tools to accomplish this method from the Ministry of Food and Drug in Korea. Method summary, so the Hydra 2C combustion analyzer demonstrated that it was an effective tool for this type of analytical process, the L-cysteine extraction solution. And again, I mentioned I used the mechanical or the external dryer with magnesium perchlorate, and then all the optimization process of the instrument really helped me dial it in to make sure my quality control and both ranges were well within analytical results and requirements to make the method work really well. The sample time was approximately 6.5 minutes from loading the boat into the system, injector forks in, to dropping the boat back into the rack, the sample rack. So it's really, really fast. 6.5 minutes per analytical number is not too bad on the analytical side. So the references for this is World Health Organization, and again, the Ministry of Food and Drug Safety of Korea. That's the method, the notice, and the method methyl mercury test, and then US EPA 7473, which is mercury in solids and solutions by thermal decomposition, amalgamation, and atomic absorption spectrometry, revision 0, February 2007. So with that, I'm going to conclude the webinar. And as was mentioned earlier, you can submit your questions. I believe they're captured in the submittal form on your side of it. And then what I will do is I will address the individual questions, and or if there's enough of them that are the same, or I think it's warranted, what I might do is I might do an FAQ, and then we'll get our Marcom group to send out that frequently asked questions around this method, and then we can go from there. But happy analytical times, everybody. It was a lot of fun doing this method. I guess if you can say that analytical methodology is fun, but sometimes it is. You know, to accomplish something and to do it relatively well, and I think it would ease a lot of tension in the laboratory to have a second source for confirmation of methyl mercury, because the other methods that are out there, there is some issues with coelution of, say, inorganic mercury with the sodium tetraethyl borate method and so forth. So is some issues with that, but this, I believe, probably overcomes some of that. Albeit I did not do any test spikes with methyl mercury or any of the other bad mercury, simply because I didn't want to get involved with that, and we have a known value on this CRM sample. So with that said, I want to thank everybody for attending, and I am here if you need to speak to me and or ask a question. We'll get it answered as soon as possible. Again, thank you for attending.